5.3 Fundamental Theorem of Calculus. Read through the essential questions to see what we're going to be covering in this lesson. Take time to look at the historical perspective of the Fundamental Theorem of Calculus, the breaking ground on the information, and the two mathematicians that added so much to what we use as its results. In this screen, we're reviewing the screencast from before, where we use the area accumulating function, inputs and outputs, to find points and then go ahead and connect the points to take a look at the function. What we would like to do is to find the derivative of this area accumulation function. And in order to do that, let's review the definition of a derivative. And the definition of derivative is right here. It's the limit of the average rate of change as the interval gets closer and closer to 0. And that's what we're going to try to do. We're going to do this by looking at the two area accumulator functions, g of x and g of x plus h. G of x represents the area from a to x, and g of x plus h represents the area from a to x plus h. So what we're going to do is, just like we did with the derivative, we're going to find the average rate of change. So we're going to subtract the two area accumulating functions, and when we do that, that's going to be this area right here, which is approximately a rectangle area, and the height will be f of x and the width will be h. If I go ahead and isolate f of x, I'm going to have this, looks very much like the average rate of change. So the derivative is going to be the limit of this difference quotient, and this is going to represent f of x. Let's go ahead and go through the proof again. Again, remember that this represents the area accumulation from a to x, and this represents a little difference between these two areas. What we're going to do is what I was alluding to before. We're going to take the difference between the two areas, which is the integral from a to x plus h minus a to the x. We're going to take this integral and we're going to divide it, use properties of integrals, and we're going to go from a to x and x to x plus h. So I've taken this integral and I've written it as 2. Now when that happens, we're going to be able to cancel and simplify into this. So this difference between the two area accumulators amounts to this, which represents the area of this rectangle. And the area of this rectangle can be represented, let's see, the area, if I divide both sides by h, so divide this side by h over here, and then times by 1 over h. I'm actually doing the same thing to both sides. Let's see what happens. Okay, so this little sliver of area right here is going to be between a minimum value and a maximum value, where I choose the minimum value in this little interval and the maximum value in the interval. And this m is the lowest or the smallest height, which I'll call f of u, and capital M represents the biggest height in that interval. And we're going to divide everything through by h. So now I just have f of u and f of v. So this average change is between that. And then I'm going to substitute for this, and I'm going to write the difference quotient right here. Now, as we allow h to get closer and closer to 0, it's going to get close as this value gets closer and closer. This height gets closer and closer to f of x, just the height of that one little thin rectangle. And same thing happens to the maximum. It's getting closing in smaller and smaller, so it gets just close to that height. So both the left and right are approaching. So this limit right here is going to approach f of x because it got squeezed. And remember what this represents. It represents the derivative. So what we've proved is when you take the derivative of the area accumulator, you get f of x, which is the curve. And so this is the fundamental theorem of calculus, part 1. When you take the derivative of the area accumulator, you get the function back. Okay, let's see if we can't do this in this example. I would like to take the derivative of this area accumulator function, and so that derivative will be this function. And this function, remember, this is a dummy variable t, and the function's an x, so I'll just write 1 plus x squared. Okay, here's an example of taking the derivative of an area accumulator as well. Notice there's just something just a little bit more difficult in that that top limit is not the variable x, it is x to the fourth. So we're going to take this more complicated upper limit and write u, and we're going to take the derivative with respect to u, understanding that we're going to have to use the chain rule. So we're going to take the derivative of this will be secant u times du dx. Now remember what u was equal to. U is equal to x squared, so I resubstitute and I take the derivative of u, which is 4x cubed. All right, here are some opportunities for you to take the derivative in each case. Take a minute to stop the screencast and then check your work. Here are the answers. Let's take a look at Fundamental Theorem of Calculus, Part 2. This says if f is continuous on the closed interval from a to b, then the definite integral from a to b of f of x dx is equal to the antiderivative of the upper limit minus the antiderivative of the lower limit. We did prove this before, but let's take a look at it again. All right, so we know this is an area accumulation function, and we are aware now that this is an antiderivative. So capital F of x is the antiderivative of this f of x over here, and that's also equal to g of x. We know that by the properties, g of a is going to be the area from a to a of f of t dt, which is going to be 0. So let's go ahead and start with f of b and f of a. Remember, f of b is an antiderivative, so it's g of b plus c minus, and this is an antiderivative, g of a plus c. Now the c's are going to cancel, and we're going to get g of b minus g of a, which is equal to, now remember, this is 0, so this is g of b. And g of b, remember, is the area accumulation from a to the endpoint b of f of t dt. And you're really used to seeing it this way, where the integral is first, and it's equal to the antiderivative evaluated at the upper limit minus the antiderivative at the lower limit. So we're kind of going backwards. All right, we're going to use these results when we're taking a look at area under a velocity curve, and the antiderivative velocity is position, so we'll take the position at the upper limit minus the position at the lower limit. Okay, let's go ahead and evaluate this integral. I'm going to go from 1 to 3 of e to the x dx. So I'm going to find the antiderivative of the function, which is e to the x, and I'm going to evaluate it from 1 to 3. So this will be e to the third minus e to the first. And we can leave it that way to be exact, or we can put it in the calculator and get an approximation. Let's go ahead and find the area under the parabola. We did this with brute force, and now we're going to be able to use the fundamental theorem of calculus. So the antiderivative is x cubed over 3, evaluated from 0 to 1, and then this will be 1/3, take away 0 over 3, and so the answer is 1/3. We did it with brute force before, and now look, the fundamental theorem of calculus allows us to go a little faster. Here's an evaluation from 3 to 6. Take a look at the solution. Take a look at that you need to find the antiderivative, which is a natural log. We can drop the absolute value sign since our limits of integration are all positive. And we go ahead and evaluate it, and there's our answer. Find the area under the cosine curve. They say the area is 1, and I went ahead and showed you in calculus notation how to find it, how to find the antiderivative, evaluating from 0 to pi halves, and the answer is 1. That might be surprising here. What's wrong with the following calculation? Think about it, stop the screencast, think about it, and then look at the answer. And the answer is 1 over x squared is not defined at x equal to 0. This condition, the condition to use the fundamental theorem of calculus is differentiability and continuity, and we don't have that in this interval. All right, so this is a summary of the fundamental theorem of calculus, part 1 and part 2. Part 1 says that the area accumulator is an antiderivative, and part 2 says that if you want to find the definite integral, you do that by finding the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Take a minute to read this so that you look at it. This is probably the pinnacle of this whole course, is the fundamental theorem of calculus. It relates all the concepts that we've studied. It relates limits, derivatives, integrals one kind, integrals another kind. It really pulls in everything that we've learned. All right, it's your turn to evaluate the integral. Go ahead and stop the screencast, take a look at these problems, and then check your work. And here are the answers.